Okay, I'd like to thank, thank the organizers here, especially Andy and John, for all their work and for the invitation. So I'm going to talk today about ambient metrics and exceptional holonomy. So the main result I want to talk about is work with student Travis Wilsey, who's going to be giving a talk after this one, and I'll indicate the connection with what he's going to be talking about later on here. So the main result has to do with proving the existence or giving a new construction of metrics of holonomy, the split real form of G2. So let me start with just a little review of holonomy. So let's see. So we start with a connected pseudo-Riemannian manifold, signature PQ. And to every such manifold, you can define its holonomy group. So that's a subgroup of the identity component of the orthogonal group in signature PQ. And what I'm going to be defining is usually called the restricted holonomy group. It's a subtlety that'll just be built into my definition, so we don't need to worry about what the other versions are. So the holonomy group of the pseudo-Riemannian manifold is all the linear transformations obtained by parallel translation around contractible loops. So specifically what I mean is that you take a point of the manifold and you take a contractible loop based at that point. You start with a tangent vector at the point and you parallel translate it around the loop. You get back to the same point and you get possibly another tangent vector there. And that defines a linear transformation from the tangent space at the point to itself. And the set of all the linear transformations you get that way is a group, and that's the holonomy group at that point. Since the metric is parallel, that linear transformation has to be an orthogonal transformation for the metric. So we get a subgroup of the orthogonal group in that signature, and then let's see, and then the group is always connected because my loops are contractible. And so then you choose a frame. Using the frame, you can identify the tangent space at the point with Rn, and you can then transfer the group to just be a subgroup of the basic identity component PQ. And the subgroup you get is independent of the frame and independent of the base point up to conjugacy. Okay, so that's how the holonomy group is defined. So what it does is it measures the structure on the manifold preserved by parallel translation. I mean, it's parallel translating things, so any structure that's preserved by parallel translation is going to restrict the holonomy to be in the group of things that preserve that parallel object. So the smaller the holonomy group, the more structure is preserved. So if you pick a random pseudo-Riemannian manifold, I mean, just pick one at random, most of them are going to have full holonomy. I mean, generically, the holonomy is going to be everything, because most pseudo-Riemannian manifolds are bumpy and they don't preserve any structure when you translate around them. So you can look at special holonomy classes just as a couple of examples. So if we're in even dimensions with positive definite signature, then the holonomy is a subgroup of the unitary group if and only if the metric is Kähler. And that's because Kähler metrics are, one of the definitions is that they have a parallel orthogonal almost complex structure. And since it's parallel, that's going to be preserved under the parallel translation, and it's going to force your holonomy transformations to be unitary. Okay, and then the other extreme is when a holonomy group is trivial, and that happens if and only if the metric is flat. So if you're in Euclidean space, then you take any vector in Euclidean space, it doesn't move at all when you parallel translate it. And if it's flat, that's still true. So those are just some examples to illustrate what happens with holonomy. Okay, so if you start thinking about holonomy, one of the first questions that you think of is, well, what subgroups can arise as holonomy groups of pseudo-Riemannian manifolds? What are the possibilities for the ways the holonomy can be restricted? So I'm going to restrict to, or people restrict to looking at certain subgroups which are sort of basic building blocks. So we'll say that a subgroup of the identity component of the orthogonal group is irreducible if its action on Rn has no non-trivial invariant subspaces. So you just let it act by matrix multiplication, and that's an irreducible action. So
Is there a Dorama decomposition for manifolds?
That's a really good question, and the answer is no. That's not known, and I was hoping to avoid that subtlety. But I'm going to, so what she's getting at is that, that in positive indefinite signature, then there's a Dorama decomposition which says that if the group splits as a sum of groups that are irreducible, well, say if they're irreducible, then the manifold itself splits as a Riemannian product. So there is no such theorem, and for that reason, that the list, everything I'm going to say is true, but it's not really what you want to be considering in the mixed signature case, as far as classifying what all the possible holonomies are. But still, the irreducible ones could certainly still be regarded as some basic building blocks, and that's what we're going. That's just the point of view that we'll have here. Okay, so. In 1953, Berger derived a list of irreducible subgroups. For every P, Q, and N, there's a list. So you fix your dimension, you fix your signature, you get a list of groups, and they're all irreducible. And this list has the property that any group that can arise as a holonomy group has to be on this list. So it just restricts the possibilities that you can have. So every irreducible subgroup which arises as a holonomy group for some pseudo-Riemannian manifold has to be one of the ones on this list. So what this does is just rephrases the question, does every group on this list arise as a holonomy group? He says you only have to worry about the ones on this list. Okay, so that's Berger's list. Now, back when the list was made, people looked at the groups on the list, and a lot of the groups, examples were known, like the unitary group of metrics that had that holonomy. Okay, so many examples were known, but there were some groups on the list that nobody knew whether there were metrics that had that holonomy or not. So one of the things you notice when you start looking at this list, so I'm not going to write it down because it's full things on the list are not relevant for what I'm going to need, but you notice one thing, that of course in every signature and every dimension, the full identity component of the orthogonal group is on the list, because it's the generic thing. Almost all the other groups you see on this list only occur in even dimensions. So this is one thing that you notice on this list. So there's only two exceptions. There's only two groups for any signature in any dimension on this list that occur in odd dimensions, other than the full group itself. Okay, and these examples both occur in dimension 7, and they're the two real forms of the exceptional Lie group G2. So G2, if you don't know about G2, the next slide will be a little mini introduction to G2. There's two real forms, G2C for the compact real form, so that's a subgroup of SO7, and then the split real form is a subgroup of SO34. So other than the full groups, these are the only possibilities that can occur on Berger's list in dimension 7. And these were two examples for which nobody knew whether or not there were groups that had this holonomy. So this existence question was stayed open for 30 years, more than 30 years, and it was solved by Robert Bryant in 1987. And he showed that there exist metrics whose holonomy is both G2 compact and other metrics whose holonomy is split G2. Okay, so the compact G2 has been of a lot of interest recently because it comes up in string theory as an odd dimensional version of Calabi-Yau manifolds for the little compactified dimensions. So these have been of interest in recent years, and there have been more constructions now of metrics of these holonomies, compact and split G2, but they're not easy to come by. It's not easy to come by examples, and new examples are of interest. So. They're both. He had a sort of a general machine that produced some examples, and he wrote down some completely explicit examples as well. Okay, so.
Instructions of Joyce, did they work for both the compact form and the split?
No, the point of those is to make compact examples. So yeah, I think that's in the compact case. Yeah. Okay, so a little one-slide introduction to G2 here. So to think about this definition, I'm going to give, just think about how you define orthogonal groups. Right, so you want to define orthogonal groups, what you do is you pick a quadratic form, you classify them under the general linear group, and they're classified by their signature. And then for each signature, you look at all the linear transformations that preserve one of those quadratic forms, and that gives you your orthogonal group. So we're going to do exactly the same thing for G2, except instead of starting with a symmetric quadratic form, we're going to start with a skew-symmetric cubic form. Okay, so suppose we start on R7, we just take a skew-symmetric 3 form, call it phi. So the reason this only works in dimension 7 is the following construction. Out of a 3 form on R7, you can invariantly define a quadratic form out of this 3 form as follows. So there's a quadratic form defined in terms of phi. So x and y are just vectors in R7. So you contract x into phi, and that gives you a 2 form. And y into phi is a 2 form. You wedge those, you get a 4 form. You wedge with 3 phi, you get a 7 form. So that's some multiple of the volume 7 form on R7. And the multiple is clearly a bilinear thing in x and y. And it's symmetric because 2 forms commute when you interchange the x and the y. So that's a canonical way of defining a 2 form. So we'll say that our 3 form is non-degenerate if we get a non-degenerate quadratic form when we do this. Right? So that's a natural way of defining a non-degenerate 3 form. And so there's a theorem, it's just an analog of the classification or an analog of the signature. So if phi is non-degenerate, the only possible signatures up to plus or minus that can arise for this quadratic form are either the definite case 7, 0 or the split case 3, 4. So it's impossible to start with a 3 form and get a quadratic form that has signature 2, 5 or 1, 6 coming out of this. This is a linear algebra thing. So in the case where the signature is 7, 0, modulo plus or minus, I'll say phi is of compact type. And I'll write phi c for forms of compact type. And then in the other case, I'll say it's split type if the form has signature 3, 4, and I'll write phi s for split type 3 forms. Okay, so that's the analog of the classification of quadratic forms by signature. So now there's another theorem that says up to the general linear group, these are unique. So equivalently, any through 3 forms of compact type are equivalent under a change of basis. And same thing for forms of split type. So there's really only one. Up to conjugacy, up to the general linear group, there's only one of these. So we might as well, you can pick your favorite one. Most people write one down and say, here's the definition of G2, but you can pick whichever one you like. Doesn't matter. And so then we just define the groups, which are the groups that preserve this algebraic object. So the compact G2 is the subgroup of the general linear group that preserves a compact form, and then the split G2 is one that preserves a split form. So these are subgroups of SO7 and SO34. Okay, so that's our little mini thing about G2. So in the rest of my talk, I'm only going to be talking about the split form. Okay, so from now on, G2 will be the split G2. I'll just write G2 from now on, but it's always going to be the split form. Okay, so next ingredient in this construction are going to be 2 plane fields in dimension 5. So we have there's a number of ingredients that go into this construction. So I'm going to build these ingredients. So we're starting here now with a distribution on a 5 manifold. So M is a 5 manifold. We've got a rank 2 distribution on this 5 manifold. So you know that one of the first things you ask about a distribution is whether or not it's integrable. So that means whether or not the commutators of sections remain in there. And I'm going to be looking at the case that's relevant here is the maximally non-integrable case. So we start with a local frame, and then we look at the commutator. And we're going to require that at every point, the commutator is actually linearly independent from the original, the first 2 vectors. So it never lies back in the tangent space. And even more is true if you look at second commutators. So if you take commutators out of these 3, well, we've already done x and y to get z. So you only have 2 left that you can do, x with z or y with z. So the definition is that the 2-plane field is generic if at every point the x, y, its commutator, and these 2 second commutators are everywhere linearly independent. Right? So then this is a generic condition. I mean, if you take a general 2-plane field and you perturb it, generically it'll satisfy this condition. So this is the generic case. Okay, so unlike integrable distributions, which have the property that they're all locally equivalent, these generic 2-plane fields have local invariants. So there are ones of these that are not equivalent under any local diffeomorphisms. And so Elie Cartan studied the equivalence problem for these two-plane fields in 1910 and solved it. It was one of his tour de force solutions of his equivalence problems. And so solving it means he constructed a principal bundle and a Cartan connection in the sense of the equivalence problem that solves this problem. So what he discovered is that this group split G2 actually arises naturally in the study of this. In fact, that's the model case for one of these is a homogeneous space for G2. So the model is a homogeneous space, G2 mod P. So P is a particular parabolic subgroup that I'm not going to write down explicitly. And the space, the homogeneous space, is diffeomorphic to S2 cross S3. So that's our 5 manifold. So to say that's the model space means in particular S2 cross S3 has a model, a basic two-plane field D. And of course G2 acts on it. It's a homogeneous space and it preserves this model distribution. So I'm not going to, there's some really nice math that comes in describing defining and describing this model distribution. You can look at it purely algebraically. It can be defined in terms of the algebraic structure of the split octonions. It can be looked at geometrically. It can be defined as a non-holonomic distribution for two balls rolling on each other without slipping or spinning. There's lots of great math there, but I've only got 45 minutes. So I will write down what it is in local coordinates on the next slide, what this model.
What's the Cartan generality of this? How many functions of how many?
Wait till the next slide. I'm going to write this down on the next slide. Yep. Sorry? Just a moment. Okay, so I'm not going to write down this distribution on S2 across S3, but I will tell you what the action of G2 on S2 cross S3 that preserves it is. In fact, you already know that if you were paying attention to Mike's talks. So recall G2 is a subgroup of SO34. That was how we defined it. And SO34 is the conformal group of S2 cross S3 with the metric on S2 minus the metric on S3. Right, so Mike was really talking mostly about positive definite signature where you just have Sn and its conformal group was SOn plus 1, 1. But if you do conformal geometry and signature PQ, the model is SP cross SQ with the difference of the metrics, and then your conformal group is SO P plus 1, Q plus 1. And the action of SO34 on S2 cross S3, you just realize S2 cross S3 is the space of rays in the null cone. Mike had a slide about this in the definite signature. And then SO34 just acts linearly on rays, preserving the null cone, and that gives you this action. Okay, so that's the action. And G2 is just viewed as a subgroup of SO3, and it acts on SS2 cross S3 by the restricted action. So it really is the conformal action. Okay, so that's what I said. The action is just the restriction of the conformal action. Okay, so in particular, that means that since any local diffeomorphism, I mean, the part of the equivalence problem is even local maps that preserve your structure have to be in your global automorphism group. It means even locally, any diffeomorphism preserving this model distribution actually is a conformal transformation. It preserves this conformal structure on S2 cross S3. So one can regard the conformal structure as sort of coming after the distribution. Anything preserving the distribution preserves the. So Pavel Narovsky realized that this construction worked also in the curved case. This was a really remarkable observation. What's really most remarkable is that Cartan didn't notice this because it's just sitting there once you make this realization, and he was on top of all these things. But anyway, it wasn't until 2005 that Narovsky realized that if you start with any generic two-plane field in a 5-manifold, then there is an invariantly defined conformal class of metrics of signature 2, 3 that is associated to that two-plane field. So any map, any diffeomorphism that maps one D to another one is going to preserve the conformal transformation, the conformal class of metrics. Okay, so this gives us an interesting class of conformal structure. So this was sort of Narovsky's real insight here. So we want to write these things down fairly concretely, both the distributions and the conformal classes. So this is what Maciek was asking about. So there is a explicit realization, a normal form for these distributions. So just before I show it to you, just remember, if you're asking for what's a normal form for integrable distributions, You just can take any 5 variables and you take ddx and ddy, and that they're all integrable, so they're all just in local coordinates. So you can just straighten them out. Of course, this is not going to be true here. So, yeah, all right. That's what I get for talking before I punch my thing. So one last word about Minkowski's theorem. The proof is just immediate. Once you have the Cartan connection, this is just an immediate consequence of the Cartan connection. I mean, it's you just and the fact that G2 mod P is SO34 mod its P, because those are both S2 cross S3. Once you have those two facts, you just immediately deduce that you have this conformal structure. So anyway, that's why it was something that's really sitting there. Okay, so here's the normal form. So for any distribution, you can choose local coordinates. So you write them x, y, z, p, and q on your 5 manifolds. So the distribution takes the following form. So the first one we can always straighten out. So the first one we just take to be ddq, one of our coordinate vector fields. And then we can't just do dx in the other one. So what you can do is you take p and q are 2 of the other variables. So you have dx plus p dy plus q dp. And then there's one arbitrary function. Remember, we have to have a lot of inequivalent ones of these, and so this is the answer to the question. There's a single arbitrary function of 5 variables that enters into the normal form for these distributions. So that's right. So the question is how unique is the f, and that's right. But you can put it into such a form. That's right. And if you take a distribution given by this formula, by this expression, then if you check what it means for this to be generic, you write down the commutators, what you get is it's if and only if this function f has second partial derivative in q non-vanishing. So that's exactly what it means for this to be a generic distribution. So this is the problem with these Beamer talks. You have to remember this identification. I mean, you don't need to remember the formula, but you got to remember from now on I'm going to be parameterizing distributions by just choosing a single function f of 5 variables. So I'm going to write down f's, and what I'm really meaning is I'm taking the distribution given by this formula in terms of the f.
So in the homogeneous case, can you take that to be something like q squared?
Any other questions? Okay, so I told you before I wasn't going to tell you the general formula, the geometric definition of G, but here's what it is in local coordinates, of the distribution in local coordinates. And of course, q squared has non-vanishing second derivative everywhere, so that's just great. Okay, so the point of doing this, one of the points is to make this very concrete and explicit. So Minkowski actually went through this derivation, how you get the conformal structure. I mean, I said it follows immediately, and that's true, but actually to turn that into a formula, you've actually got to crank through the whole equivalence problem prolongations to get a formula for this metric. So it turns out the metric depends on f and its derivatives through order 4, up to order 4, and you wouldn't want to do this by hand. So the formula has approximately 70 terms in it. It takes basically a page to work out. He did it all with Mathematica. He actually uses this. I mean, he does everything on Mathematica, of course.
I think you can see this conformal class without doing any computation, just purely geometrically.
Well, if you have the Cartan connection, I mean, you have to have something to. If you have the Cartan connection, then. Okay, well, yeah, I believe that too, but yeah, I mean, okay, we can talk about that later. If there's really simple ways. I mean, if you can see it without any computations, anyway, okay, we can talk about that. Okay, well, that'd be great. Okay, so next ingredient. Okay, we're building ingredients. Okay, so now we've got our 2 plane fields, we've got G2 back there. So the next ingredient in this construction is going to be the ambient metric. The other part of the title there. So you've heard about this some. I'll quickly review what this does for you. So the input for the ambient metric is a conformal manifold of any signature, PQ, any dimension. What it produces for you, so think of this as a black box. You give it a conformal manifold, and it produces a manifold of dimension 2 higher, n plus 2. That manifold has some structure on it. It has an embedded hypersurface, which I call G. And it also has the property that it has a metric, at least a formal expansion of a metric along this initial surface. And the metric is a metric in 2 higher dimensions, n plus 2 signatures, p plus 1, q plus 1. So this is a black box that, given a conformal structure, it produces a manifold of 2 higher dimension with the submanifold and at least a formal expansion for a metric along it. So let me briefly, because a little bit of the structure is going to come in, let me briefly just run through how this is constructed. What you do out of the conformal manifold, you first construct the hypersurface. Right? So the hypersurface is usually called a metric bundle. So at each point of the manifold, you don't have a metric, you've just got an array of possible metrics you can choose from. And that defines a ray bundle over the original manifold that I call G. So it's just all the points and representatives in the conformal class at that point. So a section of this is just a representative for the conformal structure. Okay, so that we've already got one dimension, right? We just got this G. Now G has dilations because it's just a bundle, it's a bundle of rays. So you can just dilate the metric and get another metric in the conformal or at that point. So it has this structure of dilations. To get the n plus 2-dimensional space, we just cross this with an interval. It's sometimes called formal neighborhoods. We're just taking G and then we're going to look at Taylor expansions and some other variable about G. So we embed G as a hypersurface in the ambient space just by putting it in where you cross it with 0. And then the conditions that are supposed to define the ambient metric. So it's a metric on the n plus 2-dimensional space. Signature is p plus 1, q plus 1. And it's supposed to satisfy 3 conditions. So it's homogeneous with respect to these dilations. So it's always got a homogeneity built in. It satisfies an initial condition on G that's determined by the conformal structure. So I'm not going to write down exactly what that is, but you can do it, but just it's only got limited time. And the last thing is the differential equation that it satisfies, which is that it should be Ricci flat to infinite order. So that's the curvature condition that's supposed to determine this ambient metric. So then the main theorem, so this is something I did with Pfefferman a long time ago, 1985, is that in odd dimensions, there exists such an ambient metric, and it's unique up to infinite order and up to diffeomorphism. So it really, as a formal power series anyway, it's uniquely associated to the original conformal class. And if the background, the underlying manifold and metric conformal structure are real analytic, then the series converges, and you actually get a Ricci flat metric in some neighborhood around this initial surface. Okay, and n is even, then there's a formal obstruction at order n over 2. So you can't continue this in general to higher orders than that with smooth formal power series. That's not going to be relevant for us because we're only going to be talking about odd dimensions here. And in the flat case, just a little to keep in mind what you're thinking about. So the flat model in signature PQ I said was SP cross SQ. So in that case, what it does is just produces the Euclidean space, or Rp plus Q plus 2, with its flat metric of signature P plus 1, Q plus 1. That's what it just produces, the flat metric out of this for you. And in that case, the metric bundle can be identified with the null cone of the quadratic form in dimension P plus 1, Q plus 1. And all this fits together with the conformal group description that we've seen already. Okay, so that's the ambient metric. So now what we do is we put these together. So we're really following Nurowski. These ideas are on, Nurowski deserves, 3/4 of the credit here. These ideas were his. So we start with a rank 2 distribution in a 5-manifold. Nurowski constructs a conformal structure in 5 dimensions for us. And now we take the ambient metric of one of those and we get a 7-manifold. And it has a Ricci flat metric on it, at least formally defined near this initial surface. So again, Nurowski was thinking about this. So Nurowski knew about his construction, and actually there was a meeting in Minnesota at IMA 5-6 years ago, and I think a number of you were in the audience. I gave a talk there on the ambient metric. Nurowski was in the audience, and that got him thinking about putting these two about doing this composition of constructions here. So he thought about this. You get a metric of this signature 3-4 out of one of these 2 plane fields. And so he started playing with Mathematica and generating examples. So we're constructing 2 plane fields, like I told you, by choosing an f, choosing a specific function. Now, one way to make really sure that your f has second q derivative everywhere non-zero is to take it to be q squared plus some function of all the other variables, right? And so I really don't know what led him to, other than just trial and error and just, turning it on to run examples all night and seeing what it came up with the next morning. But anyway, he came up with these interesting examples. So you take q squared plus a polynomial of degree 6 in P plus a linear term in Z. So there's 8 real parameters here in this family. And he observed via his mathematical calculations that you can actually write down the expansion for this ambient metric explicitly. I mean, completely explicitly. In fact, the expansion terminates at order 2. It's a formal power series, but for these examples, I don't really know why. I mean, I'm supposed to be expert on the ambient metric, and I don't really know why this is happening, but it's true. The expansion terminates at second order. It's just true. You can check it. Okay? So that means you can write down the ambient metric, you can look at it, you can do things with it, you can think about its holonomy and things like that, and there's natural reasons, largely based on the flat case, to think this might be related to G2. So he got Tom Leisner involved in working with him on this, and they proved the following result 2 years ago. So you take one of these f's that's given in this 8-parameter family, then for all values of the choices, the holonomy of the ambient space. So this is real analytic, right? It's polynomial. So you get an ambient metric. It's actually given by some completely explicit expression. So it exists in some open set. And its holonomy is contained in G2 for all values of the parameters. And if one of the last 4 parameters is not 0, then the holonomy is actually equal to G2. Right? So there's 8 parameters, there's 6 A's. So if any one of those last 4 A's is not 0, then you actually get holonomy. So almost all these have holonomy equal to G2. Right? So this is and it's all explicit. I mean, these G tildes are completely explicit. So this is a 100% explicit formula for 8-parameter family of metrics of holonomy G2. Okay, so that's really good. Let me say something about the proof. So actually, we've already sort of seen holonomy, restricting the holonomy. The best way to do that is to have some parallel object. Parallel objects restrict the holonomy. G2 is defined by having as a group preserving a 3 form. So what you want is a parallel 3 form. That's the kind of thing that will restrict your holonomy to be in G2. So to show a metric in dimension 7 has holonomy in G2, what you want to do is construct a parallel 3 form of split type. So once again, they crank away on Mathematica, and okay, so on the flat model, you can. You've got to see. I mean, you've got to see. Let's see. Yeah, that's right. But then you've got to know what happens to it when you. I mean, you've got to. Oh, you got to take all its covariant derivatives, for example. You've got to do something. I mean, you've got to.
The curvature and its covariant derivative.
Right. I mean.
Well, I mean, it's got mathematical working.
That's true. That's true. I mean, yeah, you can do whatever you want. You can just write. I mean, there's lots of ways to do it.
We better start calculating parallel fields.
Yeah, I think that in this case, but because here you have to construct, and what I'm talking about is algorithmic.
Right. Once you have that metric, you can start solving for parallel fields.
Yeah. But this, well, so the point is, I don't know the recipe to construct a parallel 3 form.
No, but you just do the same thing. You just pack the equal in Mathematica and let it calculate.
And it's probably like.
Sorry.
Is it true that maybe for generic ambient metric kind of distribution?
That's theorem. That's the whole point of the talk. Yeah. Okay. So this audience is just too far ahead of me. Every question is coming up. So yeah, that's the point. That's the main theorem. Okay. So in the flat case, the reason you expect it to be related to G2 is in the flat case, the ambient metric is the flat metric, and we know that the flat metric has a parallel 3 form, which is the one that defines, on our 7 with the flat metric, the constant 3 form is parallel. So that's what motivates you to think there should be a parallel 3 form in general. So they just write it down. They use Mathematica, they crank it out. Maybe, I don't know if they did an algorithm like you're suggesting, or they were just clever. They wrote down the 3 form explicitly. That's great. I think that's fantastic, but it leaves you with the question that Igor just came up with. Well, what about other? I mean, is there something really special? It's certainly special that you can write this stuff down explicitly, but there's something special about this 8-parameter family. So that's the work that Travis and I have been pursuing. So the main theorem then is that suppose now we start with a generic real analytic distribution. We need it to be real analytic to actually get an ambient metric well defined in some little neighborhood. But yeah, is that true in mixed signature? It's certainly true in positive definite, but that's because it's Ricci flat. If it's not Ricci flat, then I don't know if you have anything that tells you that it's real. Yeah, so Einstein, anything Einstein is real analytic.
I think it's always real analytic.
Okay, well, we have someone else nodding there, I mean, shaking their head, so that's a later on discussion. Hey guys, only got 12 minutes left. Okay, so the theorem is basically the same thing. So if you start with any real analytic generic distribution, then the Holonomy is always contained in G2, always. And for an explicit open-dense set of distributions that I'll show you what the conditions are at the end, we get Holonomy equal to G2. So it really doesn't, these facts don't have anything to do with this special family or being able to write this down explicitly.
So let's see, so Robert calculated what these G2 metrics depend on locally in terms of functions of so many variables, and then you can, I mean, what percentage of the G2 metrics are you getting this way? Yeah, I get one function of 5 variables worth, but all of these have a homogeneity. These are ambient metrics, so they all have a conformal killing field of homothety. They all have so they're really coming from cones over 6-dimensional spaces. So I don't think they're producing all of them. So it really is a 5 variable. You really do get a function's worth of 5 variables.
A single arbitrary function's worth of 5, almost arbitrary. And
That is a rewrite, is what I'm saying.
Okay, so that's about Igor's question about how quasi-normal form this normal form really is. So I think there's a finite dimensional group that you have to mod out by. Right. So yeah. Yeah, that's right. No. You're certainly getting an infinite dimensional family depending on essentially an arbitrary function in terms of counting. Okay, so as I was saying, we get an infinite dimensional space of metrics, Holonomy G2, parameterized, and the data it's nice. The data is basically an almost arbitrary geometric structure in lower dimensions. Okay, so I'm going to say a little bit about the proof here, and then I'll tell you at the end about what these explicit conditions are. So there's 2 main steps. So the first step is we're going to try to construct the parallel 3 form. We first construct what it is on this initial surface. So I mean all the components of the 3 form, but only on the initial surface. And it should have a homogeneity, which is 3. And the second part of it is to extend it to be parallel, this initial data to be parallel off. Okay, so what about the first step? We want to construct the parallel 3 form on the initial surface. So clearly there's a condition that it has to satisfy, which is, I mean, if it's supposed to be parallel in the whole space, in particular, if you know it on a hypersurface, its covariant derivatives in the directions tangents of the hypersurface have to be 0, and that's a condition that on the initial data. So that's a condition. Now that condition can be reformulated. These are just words, but they're coming from Mike's talk. So I'm going to restate that by saying this object, this 3 form on G, is a parallel tractor 3 form associated to the conformal structure. The point is that this ambient connection on the initial surface is really determined just by the conformal structure on the base. And Mike actually wrote down the formula for this connection. He called it the Cartan connection, but it's just now it's also called the tractor connection, and we're looking at tractor 3 form. So this is just a reformulation of what this statement means on the initial surface. So if you're not familiar with that, it's just language. Okay, so the existence of a parallel tractor 3 form follows, again, right out immediately from the Cartan connection and the fact that G2, the big group, fixes a 3 form on R7. So whenever you've got a homogeneous space, a G mod P, if P fixes an object in some representation space, the representation space induces a vector bundle, and that object induces a section of that bundle on the space. The fact that G2 preserves it means that object is parallel, because the G2 action is what gives you the differentiations in the horizontal lifted directions. So the Cartan connection just gives you this parallel tractor 3 form. It turns out this is just for your information. This isn't part of the talk. So the other direction is true as well. So Hammerl and Sagerschnig proved that actually the existence of a parallel tractor 3 form of split type characterizes Mirovsky's conformal structures. So if you've got a conformal structure in 7 dimensions that has such a thing, it's got to have come from one of Mirovsky's. So that's very, very nice result, that the opposite direction of this. All we need is the easy part, though. Okay, so that's step 1. Now we've got our initial data. It satisfies our initial condition. The next step is to extend it to be parallel. So we prove a theorem, an ambient extension theorem for parallel. So tractor tensors just means a section of a tensor power of a tractor bundle. Okay, and now this theorem is not geared. I mean, it's motivated and completely. We got thinking about this because we were thinking about this problem. But this parallel extension theorem holds in complete generality for any conformal structures, any signature and dimension, and any parallel tractor with any symmetry. So it applies to lots of other holonomy situations. So let me state the theorem. So T is the tractor bundle of a conformal manifold. So like I said, tractor tensor just means a section of a tensor power of the tractor bundle, or it's dual because it's easier to work with cotractors. Yeah, so you're happy with Cartan connection. So you take the Cartan connection for the conformal structure. So it's a SO P plus 1 Q plus 1 mod P. And so you just look at the defining representation of P on Rn plus 2, and that induces a bundle and has a connection, and that's the tractor bundle. Okay. So the ambient extension theorem says that if you have a conformal manifold, take it to ambient metric. Suppose you've got a parallel tractor tensor of some rank. So in odd dimensions, every parallel tractor has an ambient extension that's parallel to infinite order. You can always extend a parallel tractor off the ambient space to infinite order. And in even dimensions, there's an obstruction analogous to the obstruction for the metric at order n over 2 minus 1. So in even dimensions, every parallel tractor has a parallel ambient extension. Arbitrary symmetries, arbitrary conformal structures, and so forth. Okay, so, and in the case where the data is real analytic, then this ambient extension is real analytic, and therefore it's actually parallel in some neighborhood. Okay, so this theorem had been proved by Rodgover in R equals 1. He was looking at those. These are the so-called almost Einstein structures. It had a different proof. The R equals 1 case is a lot simpler. And anyway, once you have this, you immediately conclude the holonomy is contained in G2. Because you've got a parallel 3 form, that puts your holonomy in G2. If you've got a real analytic, you've got a real analytic structure, so you get something in the neighborhood.
So this theorem will work in compact case as well?
Well, so the ambient metrics have to have mixed signature because it's a P plus 1. Even if you start with a Riemannian signature base, you're going to get a Lorentzian signature ambient metric. So you can never have a definite ambient metric. Okay, so that's the main theorem. That's the parallel. So Travis will speak after I finish here, after a little break, and so he's going to talk more about this parallel extension theorem. So the last thing I want to close with is to discuss, tell you what these conditions are to make the holonomy equal to G2, right? So we've seen that it's always contained in G2. So what do we need to make it equal? So this is the analog of the conditions one of A3, 4, 5, or 6 is not 0 in the Leissner-Norowski's theorem. Okay, so there's two conditions that come in. The first one involves the Weil and the Cotton tensor, the basic curvature quantities of a representative of Norowski's conformal structure. So we take our two-plane field, we take Norowski's conformal structure, we look at its Weil and Cotton tensor. So we define a map, a linear map, using the Weil and the Cotton tensors as a matrix defining a linear transformation. So linear transformation takes a vector and a scalar and gives us a 3 tensor. And you contract the vector into the Weil tensor in one index and multiply the Cotton tensor by the scalar in the other, and you get a tensor with 3 indices that's got some, what did you call it, hook symmetry? Hook symmetry. So this, in any case, this is just a map from a 6-dimensional vector space, because the tangents, it's 5-dimensional manifold across R, so we got into some big vector space. And one of the conditions we're going to impose that this map is injective at some point of the 5 manifold. So that says this is a non-degeneracy condition on the Weil and Cotton tensors. They're sufficiently non-zero and sufficiently complicated that they generate a injective map when you contract with like this. Okay, so I probably don't have time to say where this is coming from. For those who know, this is ruling out metrics that are conformally Einstein. Right? If a metric is conformally Einstein, then for the conformally rescaled metric, the Cotton tensor is 0. And the way the Cotton tensor transforms is this, for appropriate lambda and v, this will give the Cotton tensor of the conformally transformed metric. And so this map will never be injective for a conformally Einstein metric. So that's what this condition is ruling out. Okay, so that's one of our conditions. The second one involves Cartan's fundamental curvature invariant for generic distribution. So when Cartan solved the equivalence problem, when you solve the equivalence problem, you get a curvature of the Cartan connection, which is some complicated object that has a lot of different pieces, but there's one basic piece. that generates all the rest by Bianchi identities. And I call it A. And Cartan identified this. So it's quite simple. It's a symmetric 4 tensor on the distribution. The distribution is a 2-dimensional vector space. A symmetric 4 tensor it's got 5 real components. Right? It's a 4 tensor on a 2-dimensional vector. It's basically a polynomial of degree 4 and homogeneous in 2 variables. Scalar polynomial of degree 4. Okay, so in classical invariant theory language, it's a binary quartic. Quartic because it's homogeneous to degree 4, and binary because it's got on a 2-dimensional vector space. D is 2-dimensional. So there's different non-degeneracy. There's a lot of invariants you can write down. Classical invariant people study these. So the one that I want to impose is that this symmetric 4th tensor is 3 non-degenerate. So what I mean by that is that this is just a non-degeneracy condition, like saying a quadratic form is non-degenerate, but now we've got 4 arguments. So it's not 3 non-degenerate if the only vector that has a property that if you plug that vector in 3 times and you get 0 for all other vectors, the only vector that does that is the 0 vector. So this is a non-degeneracy condition on the basic curvature quantity, curvature invariant. So then the theorem is that it makes the holonomy equal to G2. So if you're given a real analytic manifold with a distribution, if there's 2 points in the manifold, this is not the signature, right? So you 2 points in the manifold, and at one of them L is injective, and at the other one A is 3 non-degenerate, then the holonomy is equal to G2. Okay, in particular, you can take the P and the Q to be equal, right? So if there's one point where both of these conditions are hold at a single point, then the holonomy is equal to G2. And now you can think about this in terms of F, right? Because just think about the Taylor expansion of F. So each of these conditions, L is non-degenerate and L is injective and A is 3 non-degenerate, is an algebraic condition on the 7 jet. So it turns out these involve up to 7 derivatives. And so these are, this defines in the space of 7 jets of F, at a single point, this defines some algebraic subset, and if the 7 jet of F avoids that, at one point, avoids that algebraic set, and all the rest of the derivatives can be anything you like, your holonomy is actually going to equal G2. So it's almost all these Fs. I mean, there's just some real lower dimensional algebraic. It's even a Zariski open kind of set. So it's a weak, explicitly checkable condition on your F. And unfortunately, I don't have a thank you slide, so I'll thank you for listening.